So there are a lot of different types of robots, autonomous mobile robots and surgical robots. The ones we're going to focus on in this course are industrial robots. There's a few different types of formats. The two on the left are traditional robot arm, which has 6 joints. The one on the right is more of a, it's called a SCARA robot. I forget what SCARA stands for, but anyway, it's a different set of motions. It's more, just goes up and down and can quickly move across a flat plane. Um, so looking at robots, there are some very basic robot systems, and some of them are based on just each joint has only 2 positions. So um, this would be an example of an open loop robot system where each joint is being told to either go to one extreme or the other. And the driver on that is really just driving a sequence. So there's a driver board. It tells the actuator to move one way or tells it to move the other way. There's no in between. And there are a fair number of robotic systems that are set up like this for simple movements and positions, pick and place, that kind of thing. But to really get the sophisticated, precise movement, you have to have closed loop. Closed loop means that each of the axes, each of the joints, has an encoder which gives information on how the joint is moving or how far it's moved. So that speed and position data goes back to the controller. And so let's say the program says, okay, I want this robot to move from point A to point B at a certain speed. What the command is going to tell it to go there, and the feedback is going to tell it how far away it is, if it's getting close, and if it gets close to where it's supposed to be, it'll slow down a little bit, and then it can precisely go to exactly where it needs to be. Because with this feedback, if it's not in the position where it's supposed to be, the controller will correct either the speed or position to match what the program is supposed to be. So that's an example of closed loop control. So on an actual robot, you would have 6 of these controllers, each controlling each of the 6 axes on the robot, with speed and position data for every axis of the robot. So the basic functional block for each axis is a servo motor. It's just a rotational motor, and on the back of the motor is the encoder, which counts using, it's like a disc with slits cut into it, and as it rotates, there's an optical sensor that senses the slits going past. It can also detect, it uses an extra sensor to detect the direction, so it can tell the direction and speed of the motor at any moment, and that feedback is going back to the servo controller, which is which is commanding the motor to move to the position. So the idea of feedback is, okay, if it moves, the feedback tells the system, is it there yet? Or how far away it is? How fast do we need to move to get there? And those kinds of things. So robot is just a very big set of servos. Okay, some basic types of robot motion. The one I mentioned already is called limited sequence. That's the type where each joint has only 2 positions. Then there's a point-to-point type motion where a robot is programmed to move from point to point to point. The robots we're going to be using are that type of robot. Then there's a continuous path, which is a very smooth, curvy path. Essentially, a continuous path is like a point-to-point robot with a lot of points, so it can trace a very intricate path. So limited sequence, also known as stop-to-stop or bang-bang control, is simple kind of path control, really just used for simple motions with a few limited positions. Very often you'll have pneumatic cylinders used to control the positions. Sometimes there may be a limit switch or a sensor that detects when the joint has moved to its other position, but sometimes they're just open loop. So basically, the limited sequence control has a sequencer that just times when a joint is supposed to move, how long it's supposed to be there. Like I said, usually it's over loop, but sometimes sensors are used to provide feedback from the joints. And okay, so the point-to-point control is where the controller is programmed with a series of points and remembers those points and how it remembers not only the points, but also what type of motion to make to get from each point to each point, what type of speed, whether it's a curved motion or a straight motion. So the programmer uses a teach pendant to kind of manually jog the robot to the points that program needs to use. Goes to a certain point, maybe closes a gripper, pulls up from that point, continues, and so on. And the controller records all the coordinate values and the speeds. And then when the program is run, it just repeats back all the different points that have been taught. So like I said, that's the kind of programming we're going to be doing in this course. So point-to-point programming, is an example of 4 points that have been programming, and then the robot goes from, one point to the next point to the next point, and so on. So continuous path control, as I mentioned, it's really just point-to-point control with lots of points. So what the continuous path control does is it records the position of every axis at every moment in time and creates this huge database of positional information. So when the robot is run in its program, it basically mirrors exactly the motions that it was put through. So the paint robots that you saw early on were an example of robots that have been programmed this way. They have very smooth, curvy movements, and so this is where a painter would teach the paint spraying robot. And then the encoders on each axis are recording and moving according to the axis, and then the data, the output from the encoders, is being stored so that it can play back when the program runs. So basically what it means is going from A to B can be done using a very definite path, making particular curves. So it's not just simply a straight line. So here's another video, and this one shows an example of a painter who's moving a paint spraying robot through its motions. And see, this painter knows just how to move to get the paint applied correctly. One thing I don't like about this is he doesn't have any kind of a mask on. Not a good idea. But okay, so I'm just going to jump forward so you can see he's programming. And okay, and then here's the robot, essentially that it, remembering exactly the motions that that it was taught, and it will do that all day, 24 hours a day, 7 days a week. Okay. So programming can either be done online, which means you're programming using the actual robot, like you saw before, either a teach pendant or a lead through programming. You can also program robots offline, and we're going to be using in this course a simulator that is an exact replica of the robot, just in a simulated environment. So you can actually do quite a bit of programming in a simulated environment, and very often what's done is then the program is loaded into the real program, and it may have to be touched up or corrected at different points, but you can do most of the programming offline, and what that does is allows the robot to be available doing some other work while you're writing a program, and it just streamlines the programming time. So here's just a little diagram of a technician with a teach pendant programming a robot to do some kind of pick and place. And that's a close-up picture of a teach pendant. We're going to be using the teach pendant with the robots in this course. And then here's is a photograph of what you saw earlier, a robot that's being programmed by being moved and having its movements recorded. You notice this operator also has a microphone, and so he's able to give commands to tell it looks like a drill bit, some sort of routing bit or something, and he's able to command verbally to turn the routing bit on and off, and that also becomes part of the program. So that's called lead-through programming. And then so offline programming means you've got a computer system that has a simulated version of the robot system. You do the programming there, and then when you're ready, you load it onto the real program and then do some corrections and tweaks. But you save a lot of the robot's operational time by doing it mostly on a robot. On a computer. And this is a screen from a robot simulation. It even shows you that the simulation can tell you if the robot's going to crash into something. So that's also very useful. Obviously, it's cheaper to let the robot do its crashing in the simulated environment, and then when you get to the real robot, hopefully you've worked out those bugs and it's got the right positions. Okay, so that's just an overview of the general robotics, and so next thing we're going to get into is specifically the FANUC robots, and talk about how we're going to turn them on, operate them, and program them. All right, stay tuned.